Then we have seen that with Harris we could detect points, corners, using the first derivative. But we could also use, there are some methods that are using the second derivative. Okay, we're going to review some of them now. So how do I detect interest points or salient points from the second derivative? Essentially, the main matrix I'm going to use is the Hessian matrix, which is the matrix, in this case this notation means that I'm taking the second derivative in the x direction, this is the second derivative in the y direction, and this is the second derivative, is the derivative in x and y for building this Hessian matrix. And then what we do is, the Hessian is just looking at the determinant of this matrix. So you compute the determinant, which is this formula here, and you get a value. And essentially, if the determinant is big enough, or in fact, different methods look at what is happening with this determinant. In fact, the Baudet method is looking at the local maxima of the determinant. Okay, and the local maxima says, okay, this is an interest point. Or zero crossings of the determinant in this other method. This is again, like as we saw with Harris, this is invariant to rotation, which is a nice feature. I can just rotate my camera and take another picture, and the response mathematically is the same. Remember that quantization and other effects are still there. And there's also other techniques, like this method proposed by Kitchen and Rosenfeld, in which they're using a more complex local maxima of this function k that takes into account and combines first and second derivatives. Okay, in this case, this is the proposal that they were doing. All right, every interest point detector has different performance. You can play around with your images and see how they perform. Okay, so how about a famous one, which is the Laplacian? And then I tell you in a minute why this is famous. But essentially, the Laplacian is just taking the trace of the Hessian matrix. So it's the sum of the main diagonal of the Hessian matrix. Do you see any advantage on using just these two values with respect to using the full matrix, the determinant? There's no advantage, in fact. But the Laplacian is very well known because there's one of the methods that is being used and that you will see later in this course is the SIFT. SIFT has a detector of interest points, and the detector is an approximation to the Laplacian. Okay, it's using difference of Gaussians, which is another way. You will learn about this, but the idea is that just the core idea behind the detector of SIFT is the Laplacian. And just the Laplacian is just looking at the second derivative and just adding, second derivative in x and second derivative in y. Okay, and it's detecting some points. Thing is that you will have the chance in the lab to experience with Harris and with the Laplacian and play around and see, what is performing better for your images. Okay.